So good afternoon, everyone. And today I'll be delivering my 8th talk in Bangalore, actually, in the span of 4 weeks. This will be on study of financial and macroeconomic dynamics using multi-layered networks. Okay. And so most of the work was done in collaboration with Olindo from IIM, and he was the one to give us the data also. And my PhD student, Kiran Sharma, whose thesis was based on these things, which I am presenting now. So I gave a talk on Monday where I told that, you have complex systems in general, and there can be several approaches, to study complex systems. And on Monday, I had actually focused on collective behavior and game theory. And today I'll be focusing on more of, network tools and slightly time series analysis, nonlinear dynamics tools, okay? So this is what we will focus on, right? And I told you that if you want to have a more broader overview of these subjects, you can look at these books, which this one is a textbook, this is an edited volume, and several of the things which I'm presenting have been appearing in these series of volumes, and 2 of them have been published in the last few years, actually. So if you want the PDF files, I can send it to you or share it with you. I will be focusing on this part on how the market actually evolves and look at the correlation patterns. And we have 3 papers based on that. And the other one is like what we are trying to do is look at the economy in terms of multi-layered networks at different levels. And so sometimes we look at the stock market, where individual stock movements become important, and we construct a network of them. Sometimes we are looking at the sectors where several of the stocks belong to one sector, look at the sectoral indices and make networks from them. And at other level, we have these market indices from different countries, and we look at the correlations between them and look at the network among. So I will go into more details in the next few slides. So that is basically what we are trying to do, okay? So as you know, you can actually download the data from Yahoo Finance, Google Finance at the daily level, okay? So this is a daily level price movement for Coca-Cola, and this is for McDonald's. And what you do is you calculate the log returns, so that they become normalized. And it's as if like if I invest 1 rupee today, what is the return I'm getting tomorrow? So if it is 1 rupee 20 paisa, then I get 20% return. If it is 80 paisa, then I have a loss of 20%. And then these also become, mean stationary because the prices are normally a non-stationary process. Now what we do is when we have different companies and their stock prices, stock returns, we calculate the correlation coefficient between them, okay? So how are they correlated to each other? And what we see is, the correlation coefficient distribution changes over time. So we have 32 years of data for 194 stocks of the US SP 500. And you will see that the cross-correlation distribution changes. And often it is very skewed and the mean is changing, okay? Now, if I look at these frames, so what I have is actually 194 by 194 correlation matrices formed from these cross-correlation coefficients, which always lie between -1 and +1. And what we have done is we've grouped them according to the sector which they belong. So some are from utility sector, some are from IT sector, some are from energy sector. But you will see that over time, the cross-correlation changes very drastically. And sometimes the market extremely correlated, okay? And if you plot the mean correlation, this is how it will fluctuate over time, okay? And these high peaks actually correspond to the market crashes. So it is of course known that when there is a crash, the market becomes very correlated, okay? And we say that this is perhaps a better way of defining a crash, because if I just look at the returns, so this happens to be the 1987 Black Monday crash. So there is a huge fall, almost close to 20% or around 20%. And there are other crashes in between. We will see that market becomes volatile in certain places, it's calmer in certain places, and sometimes even a few percentage can actually determine what a crash is. So there is no definition when we call it a crash and when we don't call it a crash. And what we are saying is that if you look at the mean correlation, that is probably a better indicator. And also, if you look at the cross-correlation coefficient, the distribution of them, and you look at the Gini inequality, so if it is less unequal, that means all the cross-correlation coefficients have similar values, and that means all of them start behaving in the same way. Okay, and so you will see that during these crashes, all of them start behaving in the same way as is being shown by this. Okay, so what we are seeing is that the market evolves and the cross-correlation structure changes very rapidly. Okay. And we are interested in these movements of this cross-correlations. So there were two physical review letter papers in 1999, which actually dealt with the noise dressing of the correlation matrices. Because when you have a correlation coefficient and a correlation matrix, many of them actually correspond to almost like behaving randomly. But there are others which you see that deviates from the random matrix formulation, and these are the ones which give you information about the sectoral or group movements. Okay, and you can actually find out more about these groups or sectors. So two papers were produced by the group of Jean-Philippe Bouchot and the other one by Jean Stanley, and this paved the way for a series of papers and investigations. So what we do is, suppose my prices or returns were completely random, and so I would have different time series. Okay, this is time series I, this is time series J, and these are all random time series. Now ideally, the cross-correlation coefficient between one random time series and another random time series should be 0. But due to the finite length, if you take, for example, n of these time series and of length 10 times that, so 10240, you will find that the cross-correlation coefficients have a broad distribution around 0. Okay, so what happens is these are spurious correlations. Ideally, if I have random numbers, there should be no correlation coefficient, right? You understand that? And you see that as you increase the length of the the time series, this distribution becomes narrower and narrower. So ideally, when t goes to infinity and 1 goes to infinity, I would get a Dirac delta function around 0. Okay. Now, what is interesting is that the eigenvalue distribution corresponding to these correlation matrices, they are much less sensitive to the length of the time series. Okay, and you see that this remains unchanged. Now, it is known, actually, this form is called the Marchenko-Pastur distribution, which was shown by two mathematicians, Russian mathematicians, in the 60s. Okay, and they worked out analytically that if I have random matrices, what would be the distribution, what would be the value of the lambda min or the lambda max, and how would it be distributed? Okay. Now, yes. Yes, because in the Wigner-Wishart you have a semicircular form. The Marchenko-Pastur you'll get only if it is completely positive. If you have, otherwise it's the Wigner-Wishart. Now, if I take the empirical correlation matrix, so I have these 194 companies of the USA stock market, and I see that, averaged over 32-year period. So this is averaged over a very long period. So you tend to lose a lot of information. But if I look at the eigenvalue distribution, as before I was telling, this corresponds to this Marchenko-Pastur. This is blown up here, so you can fit it with the Marchenko-Pastur distribution. And then there are deviations. And the maximum lambda is actually very far off. Now, the maximum eigenvalue normally captures the mean correlation of the market. Okay, and I'll show you that for intraday data. So what we do is this: we take the CAC 40, which is like the 40 top stocks in the French market, and I look at the cross-correlation coefficient every 5 minutes. Okay, and I plot the maximum eigenvalue and the next 6 eigenvalues. And in this one, I have the maximum eigenvalue and the average correlation. So you see that this is very highly correlated. Okay, so the maximum eigenvalue corresponding to the correlation matrix will give you the average correlation. Is it okay? Now, what we see is also some interesting things, that this is actually 10 o'clock till evening 4 o'clock, so 72 bins of 5 minutes. Okay, and there is a steady increase of correlation. Okay. What is also known, and I haven't shown here, is that if you look at the volatility in prices, and between 10 o'clock in the morning and 4 p.m. in the evening, you will see that the volatility goes like this. That means the markets are more uncertain when they open and when they are closing. This is because they don't know what will happen during the day, and this is because they start to panic because there are big players who have to trade a certain amount in a day, and they start making big orders, and the small individuals and other players start becoming panicky. Okay, so it drives this thing. Now, in most of the models that used to be used for stock market trading, often people would actually consider the volatility to be constant during a day, which we now know that it is not. And you see that the correlation increases steadily. So you should take into account these correlations when you are actually making strategies. Okay. Now let me come back to the random matrix theory. I was telling you if I have n such time series, okay, and each one of length t, ideally t has to be greater than n if I have to get a full rank matrix. If I take a short time series, then what will happen is that I will get exactly n minus t plus 1 zero eigenvalues. Okay, you can just work it out. Now, what happens is, suppose instead of using pure white noise, so completely uncorrelated Wishart ensemble, I use correlated Gaussian Wishart ensemble. Okay, so I incorporate certain amount of correlation within the prices. Okay, and then what happens is you'll see that this part is sensitive, slightly sensitive to the amount of correlation which is given by this U, and the eigenvalue distribution doesn't change much, and this zero eigenvalues capture no information about the correlation in the matrix. Okay, now I will use a small nonlinear distortion, and this is the form of distortion I'll use. So I have theseCij's, okay, and what I'll do is I will keep the Cij modulus of it, raise it to some power, and I will retain the sign of this Cij. So if it was plus, it will remain as plus. If it's minus, it will remain as minus. And this epsilon is a very small thing. So here, for example, we take it 0.01. Now what will happen is, if I have a value minus 0.2, for example, it will become now minus 0.1968. Okay, so basically, if I had a distribution, which I had shown you earlier, that I had the cross correlation coefficients which are going like this, now as a result of this distortion, it will become narrower. Okay, so as if I am removing some of the noise or suppressing the spurious correlations. Is it okay? This is one thing which they had done. This was done by one of our students from GNU who went to as a postdoc and worked with Thomas Seligman, and they published this in this paper. Now what happens is, this nonlinear distortion has another effect. This zero eigenvalue, this degeneracy now breaks. Okay, and what you see is that there is an emerging spectrum around the zero, which we have blown up, and this becomes sensitive to the original correlation among that matrix. Is it okay? So earlier, I was getting no information about the correlation in the matrix. So I was having n minus t plus 1, zero eigenvalues. Now I give this distortion, and you will see that the shape of this now start changing depending on the correlation structure. Okay, and this spectrum, I call it emerging spectrum. Okay, because this was not there initially, and now it is around this zero. Okay, so I call it emerging spectrum. Now, what I do is like this. I have these matrices, and they are evolving over time. I can also look at the similarity between each of these patterns. So I define a similarity distance, and this is an L1 norm, where I take the element-wise difference, modulus of that, and I average over all these elements in a matrix. So I get one number, which gives me the distance between the correlation matrix at time t1 and the correlation matrix at time t2. Okay, so I will get huge number of these distances. So what we have is actually 8,067 data points, and I've taken windows of 40 with overlap of 20. So I get about 800 such points. Okay. Now, if I actually look at it, you will see that the similarity distance matrix looks like this. Okay, and The ones where, there are some red colors, which means they are dissimilar, they are actually the ones which correspond to either bubbles or crashes. Now, it is easier to understand crashes, but it's more difficult to detect bubbles. Okay, so we anticipate that, in Delhi, for example, the housing prices at the moment are, are in the bubble. But if I have to detect, there are very few methods which help you to detect that. Okay, so we are suggesting that this is one of the methods which you can use to detect these bubbles and crashes. Yes, Govindan.
It is sensitive to choice of epsilon?
It is. So I have taken a small value and I have slides I can show you. If I make it too larger, then this starts going and getting merged with the main Marchenko Pastur. So depending on what I want to do, if I want to look at the behavior of these emerging spectra, then I take a very small choice. When I am interested in suppressing the noise to quite a amount, then I increase this thing. So in several of our papers, we have taken different epsilon. We've played around, what is suitable for which question, and then optimized on the value of epsilon. Right. Any other question? Right. Yeah. Yes, Dipendra. It's basically a noise parameter. Okay, it's a distortion parameter. So it is what I'm saying is that once I raise to thing, this value will either shrink or this modulus goes, because it's a fraction, so it becomes smaller. So this, which was a spurious correlation, now I'm as if suppressing my noise. Okay, so yes. For prediction, I'll come to it. Okay, yeah. So I'll come back to his question. He's talking about market prediction. Okay, right. So now what I'm saying is that this is historical data. What he's saying is that I am seeing that yes, during such dates, the market was very different, and I am being able to locate it. Okay. Now let's do one thing. I have those distances which I said I was calculating. Now these distances I can plot in the form of a map using an algorithm which is given in computer science, and it's called multi-dimensional scaling map. Okay, so what it does is if you have a distance matrix, okay, you have distances, and so suppose I give you the distance between Delhi, Kolkata, Delhi, Mumbai, Delhi, Bangalore, Delhi, Chennai, and so on. Okay, this algorithm will give you a set of coordinates which will satisfy that distance matrix. Obviously, the coordinate choice is not unique, because if I just translate or I rotate, the distance matrix remains invariant. Okay, but you will see that all the similar objects which have shorter distance will be placed in closer to each other, and all the ones which are far apart are very dissimilar. Okay, now I was getting these patterns, correlation patterns. I was computing the distances between them, and what I'm doing, I'm putting it into this map. So I can either put it in a 2-dimensional map, or I can put it in a 3-dimensional map. Here I put it in a 3-dimensional map. So it gives you X, Y, Z coordinates, and each one of these points correspond to a correlation matrix. Okay, and you can see basically, I've made a movie that there are groups which are placing the similar patterns together, right? Now, if I look at what are these patterns, you will find all these magenta color ones are these patterns. All the blue ones are similar to this. All the green ones are similar to this, and all the black ones are similar to this. Okay? So I have these correlation patterns. I compute the distances between them, the similarities, and then I use the multidimensional map to project it in 3 dimensions. And then what I do is I use a clustering algorithm to see that, which are similar to each other. Okay, and then I'm just randomly picking each one, but I can show you later. Now, all these magenta ones will be very similar to these, and these are the ones which are corresponding to the crash period. Okay, now I can as if call them that these matrices corresponding to these are certain states of the market. So when the market reaches this, it's actually a very critical state. There's, it's actually in the crash, and this will be a near a crash. Okay, so I can as if see that there are 4 states in the US market. Now, we repeated this analysis for other markets such as Japan, India, and we find that the number of states actually varies. So it is not always 4 states that we have. Okay. Now, once I know that there are 4 states, I can go and look back in the history because I have the correlation matrices, and I can tell that when is that market in and which state it is. Is it okay? Because I have the matrix, so I look at which state it is, I go and plot it. And then what I do is I check, how many times does it go from state 1 to state 2, S1 to S3, S1 to S4, and so forth and so on. So I can count and I can get these transition probabilities, right? And then you can plot it in the form of a network, and you'll find that, okay, from S1 to S4 is very low probability. Okay. Similarly, from S2 to S4. But from S3 to S4, there is a significant amount of probability that it will go from state 3 to state 4. Yes, yes, yes. And without fail. So one of the referees had pointed, do you get any false positives? Nothing. Okay. So we don't get any false positives. And what I'm saying is that this nature of this transition matrix will change depending on the market. For Japan, it's 5 states, but this is 4 states. Now, if I give you this information for a person who trades in the financial market, this information itself is very precious. Because if he or she knows that in the next few days or weeks, I should not invest in the stock market, I just withdraw, then I make a huge profit. So you must remember that in finance, it's when we have a crash, it's not that everyone loses money. A lot of people lose money, but there are few who always gain a huge amount of money, right? Because they are smart enough to use that information and formulate their strategies accordingly. Is it okay? So we play with the size of the window. We see overlapping windows, and we do a huge amount of computation. If you want to actually see its money, you want to formulate strategies, then you have to do a lot of more analysis. I'm just giving you a very simplified picture where I can actually say that, these are the patterns which correspond to the critical crashes or critical periods. And depending on the choice of the window, it can actually predict quite well.
So it means that if I really want to use this algorithm,
right,
I will have to choose the time of the
window. The epsilon
parameter.
Yeah.
So it will require a lot of engineering.
That's right. But this epsilon parameter is basically to look at the emerging spectrum behavior, okay, and reduce the amount of noise, okay. So for this person, if you put epsilon a little bit large, around 0.5, 0.6, we show that you get very good results, okay. And we have details in the paper, so where you will find that how the MDS, because that is telling you, during a normal period, you will have very diverse sectors. And during a crash, you'll find that all of them start behaving together. So you see one whole, circle or sphere in between. Okay. So looking at the movements in this, so I'm not going into the details of all those, but in the papers it is given. Or if you have questions during the discussion, I can show you more. Okay. Is this clear then? Now what we are saying is, as if then S3 acts as a precursor to the state. So when I know I am in state 3, I will be a bit wary or careful because I know that there might be something coming up. Okay? Fine. Now, again, I come back to that emerging spectrum. So if I take a normal business day, this is something in 85, and this is around that Black Monday, 19th October 87. You see that the correlation structure is very different. And normally your, this eigenvalue spectrum would have looked like this, but now I said that once I give this distortion and I look at these which have now become non-degenerate, you will see that the spectrum becomes like this and the other one becomes like this. So this is capturing whether you are in the crash period or not. And so what we do is we actually observe the emerging spectrum and its behavior over a long time. And this is exactly those periods when you had crashes or bubbles. Now, so what I'm saying is like this. Earlier, it was not known that the small eigenvalues, and especially the zero eigenvalues, would have any information about the market. But once I give this nonlinear distortion, I can use it to find a lot of information about the state of the market. And here I'm not showing in the details. If we have time in the discussion, I'll show you that during the 1987 Black Monday crash, the US market, it was a Monday when the crash happened, but on Friday itself, the shape started changing. And so people could have, I don't know whether they knew, but they could have used this technique. And I will show you. And I will show you that in Japan, the signal doesn't change until Tuesday. And when this eigenvalue, this emerging spectrum changes shape. Because after the crash happened on Monday in US, the news traveled to Japan, and you could see the change in shape in emerging. Yes, that's right. So what happens, we react or we panic and the crash happens earlier. But the thing is, that's why most of the traders, even if they have information, they will not disclose. Yeah, right. So that's one of the strategies, but that is what I'm telling. If I get some information that there might be something wrong, I will just quit the market. And I can save a lot of money just by quitting. If I know when to quit the market, I have done a good job. Yes, I'll ask him first. Yeah, so we are not going into the detail why the crashes are being caused. What we are trying to say is when they are doing. Okay. Now you are very right. I can show you again more pictures that in the US market, post 2000, the market has become very volatile. Okay, and that you would not be able to see only by the movements in the returns. If you do these type of analysis, and I can show you, then you can detect it. In Japan, it started becoming as early as 1990. So every market has different distinct characters, and you can actually use these tools to understand that better. Okay, any other questions so far? No. Great. So this is what I was saying, that I'm using what is called the random matrix theory in physics. And this is a very unique tool, actually, which was invented in the 1930s in nuclear physics, actually. So Gautam and other people have used it to studying, I think, how the string theory. Yes. Also in nuclear physics, they used to study and model the, energy levels in the nucleus. Okay, so it started in physics, and now it is applied everywhere, including finance and biology. Every type of system you can find that this tool becomes very useful. Oh, by the way, so I have also applied these same tools in the modeling of environmental system, and I presented it actually 2 weeks earlier. But I can show you this works very well in detecting critical states in the environmental ozone also. Okay, so if you give me any time series data, I would be able to use this technique and tell you when the system is becoming critical. Okay, so again, if somebody is interested, I can show you these results during the discussion period. Now, as I was telling you, I look at the market at the level of stocks. So I was having these correlation coefficients between different stocks. I can also construct a distance by using a transformation like this. Okay, you will see that if you make this transformation, this distance follows all the properties of a distance matrix, and they lie between 0 and 2. Once I do this, okay, I can also run what is called a minimum spanning tree algorithm, so that I have these n nodes. Okay, and I connect them with certain distances such that the sum of these distances are a minimum. Okay, and that's what we do. We connect that and we show you in details that this is the type of tree you will get. And General Electric is in the center, which is highly correlated with all of these. And you'll find that all the energy companies are in one branch, all the utility companies are in another branch, because this is basically a hierarchical clustering. But you'll see that the normal market, the structure or topology of the market is very different from a crash. Okay, and you can look at the topological properties, for example, how the degree distribution changes, and study these details. You can also apply certain things, like if I do portfolio optimization, so I'm investing in different stocks, and these are the weights. I have 110 companies over a period of almost 20 years, how the weights of my investment would vary. So you'll find that there are certain companies, for example, General Electric, which will never appear in your portfolio. And there are others which will appear. So if you go and check back, now where are they located in the tree, you'll find all these companies will never appear in your portfolio. And these ones are the safe periods. Okay. Now, instead of these stock movements, I can also look at the indices, the sectoral indices. So we looked at all these sectors across 27 countries. And I made a minimum spanning tree. So this is, for example, USA. And then I use the eigenvector centrality to understand which form the core and which are in the periphery. Okay, and if I look at the multidimensional scaling map, I find, these are the ones here, and these are the ones which are very dissimilar. And this way, I have done analysis for 27 countries, and only 20 maps are shown here. So you can see which are the sectors which are in the core, which are similar to each other, and all such things. And then I can study the sectoral dynamics. So sometimes you'll find that what was a core remains a core. So we chose two periods. One is 2008-9, which is relatively volatile period, and one is 2015-16, which is a calm period. And you'll see that some of them always remain a core. So finance and ID are always in the core. And there are sectors like TC, which is telecom, which is always in the periphery. For some countries like Canada, the structure doesn't change. There are others like Finland, France, Philippines, Sweden. Also, it's a very stable core periphery structure. You can also see, just by comparing for different countries, how are the sectors hit. So after the subprime crisis, you find that the IT sector was, severely hit in Great Britain, and other places it was sometimes affected, sometimes it was not affected. Okay, so these are the type of things you can do, and relate it also to the market cap, the revenue, the employee size, and you can show that the fluctuations in these variables are related to the fluctuation in the financial movement. Okay, so these are published in that scientific report paper. Now, if I ask that which are the sectors where you should invest, again you will find that the ones which are high in the eigenvector centrality will not appear in your portfolio. Okay, so that's a similar message. Now the final 1 minute or 2 minutes I'll take is, suppose I have the financial network. I also have a trade network and a foreign direct investment network. So I construct them, and then I look at the core periphery structure. So I've done this for the 18 European countries, and based on this eigenvector centrality, I identify which are the very core, which have smaller connections, and some are isolated. And we want to see how the movement in one affects the movement in another. Is it okay? And what we can do is we can look at the eigenvector centrality, and then with the trade or eigenvector centrality across time, so 2003, 2005, 2007, 2009, and we find that there are strong relations between them, correlations. Okay? Then you can also look at the trade and FDI, or indices and FDI, and you will see similar type of correlations. So that is the type of thing that we are trying to do using network tools. You can find all these papers either from my Google Scholar page or from my website here. And thank you for your attention.